And next up is our next featured speaker, Vladik Kononov. I nailed. I kind of nailed it. Give him some applause.
Maybe it was hardware issue after all. Okay, wow, first time on stage in over 2 years, and I have actually forgotten how nervous I can be. So my name is Vladik Kononov. I specialize primarily in distributed systems and domain-driven design, speaking of which, I have a copy of my latest book right here, Learning Domain-Driven Design. So whoever is going to ask the most interesting question is going to get it. Now today, I'm not going to speak about domain-driven design, but another fascinating subject, coupling. So here's the thing. There's one quote that lately I've been using almost all of my presentations, and I was thinking, hey, why should we wait till later? I'll just put it right there on my first slide. So here it is. Ruth Milan says, system design is inherently about boundaries. What's in, what's out, what spans, what moves between, and it's about trade-offs. It reshapes what is outside just as it shapes what is inside. And I wanted it on the first slide because it outlines the overall topic of this talk, system design, but more specifically, the relationships that span across boundaries involving the thing we fear the most, coupling. And we've always been told that coupling is bad. Coupling slows us down. It cripples our systems. When working on a code base that doesn't cooperate with us, code bases that resist changes we want to make, we are blaming it on coupling. We blame coupling for making everything entangled and impossible to change. As a result, what do we want to do about it? Well, of course, we want to decouple everything. We want to break everything apart into those tiny, tiny services or classes or serverless functions or whatever. But the motivation is always the same. We want to be able to change any one of those tiny, tiny boxes independently. But what results are we really getting by following this somewhat simple reasoning? Well, in many cases, we go from coupled piles of code to distributed piles of code. And that's not surprising, because as Matthias says, going for as small as possible is almost universally a bad advice in software design. Or as this smart man right here says, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful. And yet, we keep on doing that. So I know it may sound somewhat controversial, but instead of fighting coupling, in this talk, I want to propose a different way of thinking about coupling. And I will even try to convince you that we can use coupling as a design tool. So in the next 40 minutes or so, we'll explore the nature of that scary beast that we call coupling. We'll see what it is exactly, analyze how coupling manifests itself in different dimensions, and ultimately how we can use that knowledge to design modular systems. So, what is coupling? If we go to the lexical origins of this word, it will take us all the way back to Latin, where it was composed of two words, co and apere, coapere, meaning fastened together. In other words, if two things are coupled, they are connected. And that makes coupling a ubiquitous phenomenon. It is everywhere. This clicker is coupled to my computer. Organs in our bodies are coupled to form us, living organisms producing code. Or, in my case right now, an organism producing insane amounts of adrenaline and cortisol. Anyway, cars, computers, cities, companies, organisms, for that matter, any kind of system is based on coupling. You cannot build a system if all of its components are disconnected. That is just a collection of some parts, and simply grouping them together, it doesn't provide any value. It's just a bunch of fully independent, fully decoupled things, but that's not a system. For a system, we need these relationships, these connections between the components. Coupling makes the overarching system greater than the sum of its parts. Therefore, it makes little sense to try and decouple everything. Coupling is an inherent part of system design. So instead of trying to eliminate coupling, it's more reasonable to try and evaluate those intercomponent relationships that we have and consider if they are working for us or against us. And if the latter is the case, then we should ponder what we should do about it. Maybe we can refactor them to improve the success rates. For example, let's say we have two coupled components. The downstream references and thus depends on the upstream component. The arrow between them, that relationship, it defines how these components are integrated. It defines how a change in the upstream component is likely to break the integration and require cascading changes in other parts of the system. As Michael Nygaard says, coupling defines the components' degrees of freedom, how freely the components are able to change without affecting other parts of the system. In other words, coupling defines what changes can we make in the upstream here without being afraid to break the integrations with other components. The interfaces used for integration, they have to enable some movements or changes, but prohibit others. As, for example, here, these Lego blocks, they're designed to enable certain types of connections between them. And this clear definition of the integration interface allows introducing new shapes they can work with existing Lego blocks. Now, this may sound limiting, but actually, we don't want unlimited degrees of freedom. That would render any system overly complex and simply unusable. I don't want to be able to couple this clicker to my phone, or to my car, or to that chair. That is meaningless. It makes no sense. Unlimited degrees of freedom, it's chaos. So we want to make some integrations and changes safe while restraining those that we are not interested in. We want to align the allowed degrees of freedom with our needs and expectations of future changes in the systems we are building. And that makes coupling a first-class design decision. So going back to Ruth Milan's quote, we want to design what spans and what moves between the boundaries in a way that enables only the changes and movements that we actually need. To do that, we have to understand the dynamics of coupling, how it works and how it manifests itself. And the thing is, coupling, it's not some unidimensional thing. It affects systems in multiple dimensions: space, time, and the combination of these two, gravitational force, if you will. So let's go over them, but I have to warn you, the first one, strength, that's the heavy one. Here we're going to spend most of the time. So let's start with strength then. The effect of strength is probably the most obvious one. It reflects sort of gravitational force that pulls components together. It defines what is the impact of a change in one place is going to be on the other components of the system. The higher the strength, the more cascading changes will follow. And as our industry evolved, a number of models were introduced to evaluate strength, namely coupling in the structured design methodology and a model called Kinesence. Who here is familiar with structured design? Few people. Kinesence? Cool. And who here uses it in day-to-day? No one. Okay, cool. So let's briefly go over the levels of these models and see the differences between them. Now, there is no need to memorize all this stuff. There are going to be lots and lots of details. Instead, try to focus on the essence. What attributes of the design are reflected by these models and their levels? Later on, we are going to combine them into a more compact and usable framework that you can actually use. When you will need to memorize stuff, I'll just tell you, okay? So, the structured design methodology, it was introduced back in the late 60s. You won't find these books on Kindle, but it's fascinating to see that, today, over 50 years later, we are struggling with almost the same software design issues as they were describing back then. So back then, to evaluate coupling, structured design proposed the following 6 levels of interconnectedness. Content, common, external, control, stamp, and data coupling. Now, this terminology, it may sound somewhat unintuitive or awkward even, and that's because it is based on keywords from languages such as Fortran and COBOL. So let's see what they mean. The first and the strongest one is content coupling. And the idea here is simple. A module uses private interfaces, or in other words, implementation details, to communicate with another module. For example, today we can use reflection to get or set a value of a private field, or call a private method. And it's private for a reason. It was not intended to be used as an integration mechanism with other components. And that makes it content coupling. Modules are common coupled when they communicate through globally accessible memory space. And this shared memory space is an unstructured global byte array. Both modules have to duplicate the knowledge of how that data is structured, and there is no formal integration protocol, which makes such an integration interface quite implicit. Slightly lighter is external coupling. Here, instead of using an unstructured byte array, the modules are sharing a global variable. This variable can be a primitive or an array of primitives, and it's still a shared memory, but at least now the interface is better documented and it's a bit more explicit. Control coupling happens when one module dictates to another one how to do its job. In other words, that business logic is not encapsulated well. It should reside in one module, but it's spread across multiple modules. Stamp coupling, these modules are communicating by exchanging data structures. These records that they are exchanging, they contain much more information than is actually needed for integration. For example, I am asking for an email, and I am getting a whole customer record. Now, once I am aware of that customer record, I'm going to reference it somewhere in my code base. So next time you want to change it, well, you have to coordinate that with me. So that is called stamp coupling. Now, sharing extraneous information, it's problematic, and we're going to see it in other models as well. Another problem with it is that such integration protocol doesn't really reflect what data is actually needed for integration. It's too generic. And finally, data coupling. And this is the lowest and the most desirable level. Here, the modules are communicating by passing arguments with integration-related data only. So overall, these levels reflect how much implementation details are shared across boundaries of modules. From content coupling, in which implementation details are used for integration, all the way to data coupling, where the integration interface is both minimized and explicit. Now, these levels of coupling were introduced in the 60s. In the 90s, Miller-Page-Jones proposed a different way of measuring coupling, which is more adapted to the object-oriented programming paradigm, and he called it kinescence. This word, kinescence, comes from Latin, and it means that those elements being born together. And by born together, he means that either a change in one component requires a change in the second one, or you can theoretically postulate a reasonable change that will require both components to be modified. Compared to structured design, here we have almost twice as many levels of coupling, and they're categorized into two types, static and dynamic. Let's start with the static one. The static levels, they can be analyzed just by reading the code. These reflect compile time dependencies. And the lowest one is the sequence of name, which means that two variables need to have the same name in order to reference the same thing. For example, pass unnamed arguments to a method or accessing a specific value from a hash map. Sequence of time or of type or of class, as the name suggests, means that types of variables have to match. For example, I have to know whether I should pass an integer value or a float value. Sequence of meaning happens when conventions are used to assign meaning to values. A trivial example would be what we call magic numbers, as in this example right here. This status equals 7. The knowledge of what that magic number 7 means has to be spread apart multiple modules that are using it for communication. And that makes such interface a bit less explicit. Next one is the sequence of algorithm. This one happens when two modules have to agree on the use of a specific algorithm to understand the data that is being passed between them. For example, when encrypting the data, they have to agree on the encryption algorithm that is being used. Now, it's important to point out that we are talking about here an algorithm that they have to use. This doesn't mean that the modules have a duplicated business logic. That would be a much higher level of coupling than 4 out of 9. Okay? This is just about the algorithm that they have to agree on. And finally, the highest level of static sequence is the sequence of position. It means that instead of passing values by names, they are communicated as an array where the meaning of each value is defined by its position in the array. Such integration interface is implicit, and it makes it easy to make a mistake. If you're putting a value in an incorrect position, well, you lose its meaning. So these are the levels of static sequence. 5 compile time dependencies that reflect how explicit or implicit the integration interface is. And again, I remind you, no need to memorize this. Focus on the essence, what is reflected by these levels. The second type of sequence is dynamic. These levels can be identified by examining the runtime behavior of a system. In other words, if static sequence reflected compile time dependencies, here we are talking about runtime dependencies. And the first level is the sequence of execution. Here we have a set of operations which must be carried out in a specific order without any intervening executions in between. Just like following a recipe, we have to follow it step by step. So we have different methods that have to be executed in a specific order. There's a functional dependency between them. A higher level is the sequence of timing. And here we have an operation that should be executed in a set period of time after something else happens. For example, consider timeouting a database connection. We open database connection and if nothing happens, say for 30 seconds, we want to time out it. In that case, the open connection and timeout connection methods, they're sequenced by timing. Almost the strongest level is the sequence of value. And here we have values that have to change together, meaning that there is a business invariant or constraint which says that if those values are not changing together, the system will end up in an inconsistent state. For example, consider you have a data structure representing edges of a triangle. If you change one of the edges, other two edges have to change as well, because otherwise the triangle is not going to be mathematically correct. And that makes this data structure sequenced by value. And finally, the highest level is the sequence of identity. And here, we have two objects that must reference the same instance of another object in order to function properly. A trivial example would be two modules managing the same set of data. And that data have to reside somewhere, probably in some database. So they have to use the same database. It has to be shared. If they're going to use different databases, then they have no way to synchronize their changes. And that makes them connescent by identity. So these are the levels of dynamic connescence. The lowest is execution, in which operations have to be executed in a specific order, and the highest is identity, in which a shared object or memory space is shared between multiple modules. Now, it may seem as if we can find some parallels between the structure design's coupling model and connescence, but these models, they are actually quite a bit different. And frankly, both are quite challenging to be used in the day-to-day. First, it's not really convenient to use terminology from languages such as COBOL and Fortran, especially if you're discussing something like microservices. You can say that, well, that introduces stamp coupling. That will make you sound smart, but no one is going to understand what you want. Second, both these models have blind spots. For example, consider the case of using reflection to set a value of a private field. According to structured design, that's going to be content coupling, the highest level. However, from connescence perspective, we are setting that value. To do it, we only need to know its name. And that makes it connescence of name, the lowest level. That's not really useful. Also, connescence doesn't address extraneous data that is being passed in integration interfaces as structured design does. And finally, we have this curious case of duplicated business logic that changes for the same reasons, but it's not really reflected in any of these models. And since structured design was introduced in the 60s, connescence was introduced in the 90s, this cadence of 30 years makes now the perfect time to start thinking about a different way of assessing coupling. Now remember, I told you that I'm going to say when it's a good time to start memorizing things? It's now. So here's the integration strength, a model that I've been using for some time now, and I find it much more practical and useful. And I want to share it with you. It's basically a remix of structured design's approach and connescence, but with the focus on different levels of knowledge that is shared across encapsulation boundaries. It consists of only 4 levels: implementational, functional, model, and contract coupling. Let's go over them. Implementation coupling, as the name suggests, it means that it's synonymous with structured design's content coupling. We are using implementation details to integrate multiple modules. Needless to say that such integration method is fragile and implicit. It's easy to break the integration, and the upstream component may not be even aware of the integration happening. Next, functional coupling. This one means that the connected modules are implementing closely related business functionality. Its practical implication is that the same business requirements are going to affect both modules. They're going to trigger simultaneous changes in both components. The extreme example of functional coupling would be 2 modules implementing exactly the same business logic. When the requirements change, the modules have to change together. Furthermore, functionally coupled modules, they don't have to be physically coupled. You can have it in pretty unrelated parts of a system that are not connected in any physical way, but they still have to change together. And that makes such a relationship pretty implicit. Next one is model coupling. This one is a lower level of integration strength, and it means that components are based on the same model of the business domain. Now, this level is somewhat similar to the structured design's stamp coupling. Having to change the model in multiple components makes it more difficult to improve and evolve the model over time. Now, there is an important clarification here. the previous level, functional coupling, here we're talking more about behavior of the system, its business logic. In model coupling, we're talking more about the structure, how that business how that business domain is modeled in code, what data structures are used, and overall how it is represented. And finally, the lowest level of integration strength is contract coupling. Here, the components are integrated through an explicit integration-specific model that is decoupled from their implementation model, meaning that the implementation can evolve independently without affecting the integration contract. As long as that implementation model can be translated into the integration contract, well, whoever integrates with that model won't be affected by those changes. So these are the 4 levels of the integration strength model. They reflect the amount of knowledge that is shared across components' boundaries and how implicit or explicit the integration interfaces are. Implementation coupling, again, it shares the most knowledge about how the upstream module is implemented. Functional coupling reduces the knowledge from how to what. It focuses on sharing what is being implemented instead of its implementation details, instead of how it's being implemented. Model coupling reduces the knowledge to the model of the business domain that is being used by the coupled modules. And finally, we have contract coupling that minimizes the interface to the bare minimum which is actually needed for integration. Now, let's say that we have this very problematic level of implementation coupling. Does it mean that the design is necessarily bad? Well, that's a trick question, because to answer it, we have to explore the other dimensions. And the next one is distance. Turns out the physical location of components also affects their level of coupling. And the thing is, the connections between a system's components, they can span different distances. These distances are closely related to what we call levels of abstraction. We can have coupling between individual statements, methods, classes, namespaces, components, microservices, and even whole systems. The question is, what do we have on this vertical axis right here? So here we have levels of abstraction, but what do we have on the vertical axis? So first of all, here we have the coordination that is required to implement a change. The longer the distance between the elements that have to be changed together, the more coordination effort is required to actually make the change. In other words, the cost of making a change is somewhat proportional to the distance between the affected components. But that's not the only interesting effect of distance. It also affects the components' life cycle coupling. In other words, how interrelated are their life cycles? As the components are closer to each other, the higher the chances that changing one of them will inadvertently affect the second one. For example, if you are changing a method of a class, well, you're quite likely to change other methods as well. For example, if you changed the signature of that method. And the closer the elements are, the higher the probability for such collateral cascading changes. Furthermore, if components share the same life cycle, they have to be tested and deployed simultaneously, and that further limits the possibility to evolve them independently. And finally, the life cycle coupling is affected not only by the type of encapsulation boundaries between the components. It is also affected by the organizational structure of the company implementing them. Take, for example, 2 microservices. Let's say that they are here on the very end of this scale with the highest distance. Now, take, for example, 2 microservices being implemented by a single team versus 2 microservices being implemented by 2 different teams. There's going to be a difference. In the latter case, we definitely have higher coordination overhead and lower life cycle coupling. And thus, we have larger distance, despite the fact that we are talking about the same level of abstraction here. Now, let's say that we have this design right here. We have two systems that are connected through functional coupling. That's pretty much high on the integration strength scale. And since we have two different systems, that's a very long distance between them. So we will have a quite high coordination effort. My question is the same as previously. Is this necessarily a bad design? Well, let me ask you another question. If a tree falls in a forest and no one around to hear it, does it make a sound? No, just make vibrations in the air. That's not sound. And the same is here. If strongly coupled components never change, who cares about the strength of that coupling? And that takes us to the third dimension, the dimension of time or volatility. And the main question here is, how often do the coupled components actually change? Now, as the saying goes, making predictions is hard, especially about the future. However, we can use a tool from the domain-driven design methodology to help us identify areas of the system that are going to change the most. And this tool is subdomains. According to DDD, a business domain is composed of various building blocks. These building blocks define fine-grained functionalities that are required for the company to succeed. Technically speaking, subdomains are sets of coherent, interrelated use cases. Such use cases implement closely related business functionality, they work on the same data, and they're being changed for the same reasons. What's interesting for us is that not all subdomains are equal. There are three types of them. There are core, supporting, and generic subdomains. Core is all about the company's competitive advantage. These are inventions, optimizations, or intellectual properties that differentiate the company from its competitors. This is how the company plans to make profits. Generic subdomains are the solved problems. Here we have a readily available solution that we can just buy or adopt from open source, and it's going to be way cheaper than trying to build it in-house. And because that solution is available to everyone, there is no business differentiation here. And finally, supporting subdomains are somewhere in the middle. Here we don't have a ready-made solution, but they do not provide any competitive advantage. And so supporting domain will get much less love from the business. They will be changed much less frequently than core subdomains. And that takes us to core subdomains again. They are the most volatile. Business is interested in changing them frequently to optimize the solution, to increase the competitive advantage, and ultimately to increase the company's profits. So when evaluating coupling between components, it's important to assess the expected rates of changes. And you can do it by applying domain-driven design subdomain, by checking what subdomains you have there. So these are the three dimensions of coupling that describe the nature of a relationship between connected components. Now, let's see what insights can we gain by combining them together. First, strength and volatility. The higher the strength, the higher the probability of cascading changes. The higher the volatility, the more often we will have to take care of those cascading changes. So when both are high, we get a high maintenance effort. Strength and distance. Distancing the components physically increases the coordination effort that is needed to implement a change that affects multiple components. High integration strength over high distance makes the system expensive to change and to evolve. And distance and volatility reflect the coordination effort needed to evolve the system. If both are high, expect communication overload, frequent communication between different teams. Now, that's not the whole picture. To get the whole picture, we need to combine the three dimensions together. And combining them together gives us the ability to estimate the pain we're going to endure by maintaining that relationship. Stated simply, the maintenance pain is the integration strength times volatility times distance. Meaning that if all three are high, the pain you are going to endure is going to be high as well. Now, following this mathematical reasoning, if we don't want to endure pain, what do we have to do? We have to minimize one of them. One of them has to be 0, right? So if you can, for example, reduce the integration strength to the minimum contract coupling, then it's OK to have high volatility over high distance. Cascading changes will require lots of collaboration efforts, but the minimal strength is going to minimize the number of such cascading changes. If both integration strength and volatility are high, and there is nothing you can do about it, for example, if the components are naturally functionally coupled, they're implementing the same functionality, though, so there is no way to reduce the integration strength between them, then what you can do is minimize the distance so that when cascading changes happen, well, you don't need to invest coordination effort to make it. The components have to be collocated. They have to be close to each other. And finally, if the volatility is 0, then it's OK to have high strength over high distance. That's why, for example, it's OK to have an implementation coupling to fetch data from a legacy system. The strength is obviously high, the distance is high, but you know that the legacy system is not going to change. The volatility is 0. And that balances the coupling and reduces the pain to 0. So to sum it up, the algorithm to minimize the pain is to eliminate all accidental coupling, reduce the integration strength as much as possible, and if all fails, reduce the distance between components with high strength and high volatility. Now, let's see a couple of examples of this approach in action. And the first one shows the integration strength model. So we know that referencing another microservices database directly is a big no-no. But what level of integration strength is that? Well, it depends. If the database was never intended to be used as integration interface, that's implementation coupling. If the two components are implementing functionality that manages the data, well, they need to have one database to work with. And in that case, it's functional coupling. If, for example, the first component is a BI system that fetches data from an operational system for analysis, and the team implementing the operational system is OK with it, then they are model coupled. They're sharing the model. Operational team is going to have troubles evolving that model. Now, what if the database is intended for integration? It contains data which is formulated in a model which is optimized for integration. And the database, that physical infrastructural component, is just a method of sharing it with the world. For example, as in the data mesh approach. In that case, that's contract coupling. So if you go back to microservices, it is evident that if we decompose a monolith into microservices, we are increasing the distance between the components. Initially, they were close, so distance was minimal, and we are extending. That means we have to balance the forces of volatility and strength. Now, don't know about you, but I've encountered many cases of teams doing a POC. They were trying to decompose a monolith, and the POC was a tremendous success. But later on, when they applied the same decomposition strategy to other parts of the system, it failed miserably. Usually what happens is, when they're doing POC, they're focusing on non-business critical functionalities. In other words, supporting subdomains with low volatility. And that works. They're getting high distance, high strength, but low volatility, balanced out, no maintenance pain, everybody is happy. But when they apply the same reasoning to core subdomains, to the business critical functionalities, then suddenly they find themselves with high distance, high strength, high volatility, and a lot of pain. And that brings us back to the quote I started with. we can use this model of balanced coupling for assessing the trade-offs of different designs. As Ruth says here, these decisions are shaping not only what goes across the boundaries, but also what happens inside of the component's boundaries. And with that, it's time to wrap it up. So, in short, we spoke about coupling, what coupling is, that it's a part of system design and happens in 3 different dimensions: strength, volatility, and distance. To evaluate strength, we can use this model, integration strength, with 4 levels: implementational, functional model, and contract coupling. Each reflects the amount of knowledge that is shared across the boundaries. Distance. Distance affects the coordination effort needed to evolve the system, and it defines the life cycle coupling of the components. And finally, the rate at which the components are actually changing is also important. And for that, we can use domain-driven design's subdomains. We have to identify those core subdomains because they're going to change the most. And we have this method of balancing the 3 dimensions. If we just multiply all the 3 values, we get maintenance pain. One of them 0, and your life is going to be much better. Now, if that was interesting, look out for this book right here. It was supposed to be published about a year ago, but you know, being bad with estimates is a part of our job, so don't blame me. In the book, you can find a more detailed discussion of this approach. For example, integration strength. It also provides a way to compare designs with the same level of integration strength. For example, if 2 integrations are following the functional coupling, then there are different degrees to actually compare them. And it also provides it also discusses how we can use the same model to manage another very important aspect of software design, and that's complexity. Now, I guess we don't have time for questions, right? So
we have time for questions if these people are willing to forego their lunch.
questions, lunch?
You have a choice, people. Free food or free knowledge. Wow, none of you got up and moved. That's amazing. No, before we do get to the questions, though, we'll be back from lunch at what time? Looks at stage manager. What time is lunch finish? 2. So we'll be back here at 2. It's 12:40 now. That's an hour and 20 minutes for lunch. Yeah, now people are gauging the sense of the issue. Sorry, Vlad. But we can answer some of the questions. If I read them out, you'll answer them?
Sorry?
If I read them out, you can answer them. Here's your
Yeah,
booze,
sure.
by the way. Paid for by the
Oh.
sponsors.
Thank you.
Applause! Okay, first one is from Kevin. How do you communicate these 3 aspects of coupling to your stakeholders?
Stakeholders, if you mean business stakeholders, well, it's not their business. They should care about the business aspects. This is about how we build software. It's our job, not theirs. So I don't know. Should we communicate to them? I'm not sure, to be honest.
This one sounds like Anonymous's hopes for a relationship. Should we still aim to have loose coupling and high cohesion?
Yeah, of course. Of course. By the way, one of the levels defines cohesion. That's a homework for you. Try to find it. One of the combinations of different distances.
Thank you. And let's do the next one. Do you think these 4 types of coupling are only relevant on system level or also within a system, single code base?
Whoever asked that question, come here and get the book.
Are you giving it away for free?
Yeah.
Woo! Guys, ask more questions.
Yeah.
It's free books.
Yeah, so in the book, I discussed that this model can be applied at different levels of software, from systems to services, all the way down to single lines of code in a method. That was the idea of this model. So the book is yours.
Okay, next one from Johannes. How to cope with high coupling between front end, e.g. SPA, and back end, or how to decouple them. They often have high function and model coupling.
It depends. Sorry, but it really depends. Sometimes it's possible to introduce an integration contract that can reduce that knowledge, but I've seen cases where there is nothing that can be done, and they, in domain-driven design language, they have to be a part of the same bounded context.
Adriana asks, what's the place natural place business dependency should take in software coupling? How could we detect the dependencies to keep, the ones to change, or to ignore?
Well, I guess that the domain of the domain-driven design methodology, it's all about distilling your knowledge of the business domain, distilling what's important from what's not, so that it will be easier for you to make such decisions. Well, in my opinion, this way of treating coupling seriously doesn't really replace domain-driven design. Domain-driven design is the foundation for a lot of stuff.
Jacob says, when looking at an existing product, what dimensions should you focus on first?
Well, when looking at existing product, I would focus on 3 of them, because eventually what you want to do is to minimize the pain, and that combination of 3 of them. Now, if you're looking at volatility and you see that this product doesn't change, then okay, on to the next one. But if the volatility is high, then I would say focus on 3 of them. If all of them are equally important.
Anonymous says, when would you use anything but contract coupling?
Where you can't. For example, when you have components implementing the same business functionality, that's going to be functional coupling. There is nothing you can do about it. Same goes for model coupling. In domain-driven design language, if you are in the same bounded context, then everything is model coupling. You cannot go to contract coupling. So it depends on the context of your system. It depends on the code that you are analyzing.
Okay, we'll do one more because I'm getting hungry. But if your question is on here, Vlad's going to stand here so you can ambush him at the front. But we'll do one more. If we have high strength between 2 components, why don't we move them into single highly cohesive component?
Yeah, exactly. That's how we balance them. Exactly. We're reducing the distance. That's what happens.
Oh, that was quick. Everyone, round of applause for Vlad. If your question's unanswered, come here. He's giving away free books.
Thank you.